calculation, our three estimates, 4 subintervals. Okay. Now, tell me whether you will feel better with 8. Will those 3 approximations be closer to the real number, the exact number, if I use 8 subintervals? Yeah. Good. What about 16?
The bigger the number, the better it gets.
Good. So now, what kind of concept is this? 4, 8, 16, maybe infinity. What concept from this class fits the idea? The concept of
Sum of terms.
there's only one concept in this class that starts with Li.
Limit.
Thank you. As n approaches infinity from the sum of all rectangles, right? So if I increase the number of subintervals to infinity, and somehow I determine and add the sum of all, of course, areas. The sum of all areas of all rectangles, right? Of all rectangles. Then this will be the exact area. No doubt. So if I increase the number of subintervals to infinity, I will be able to fill in everything. I will be able to determine this with 100% accuracy if I have n subintervals and the n goes to infinity. From adding all of those areas, base times height plus base times height plus base times height, on and on and on and on. Okay, that would be the exact area. How do I write this? First of all, what it consists of? It consists of delta x, which is the base of each rectangle, times a function value, right? For this one, it was at 1/4. I'm sorry, at 1/2, right here. I was looking for the function. At 1/2, plus then at 1, plus then at 3/2, plus then at 2. Same thing here. So this will move. It will not be exact, the same value. For the first subinterval will be x1. For the second subinterval will be x2. For the third subinterval will be x3. And this key word will be exactly what I started with today. The sum of all areas from the first one till the last one. So the exact area, no approximation, is the limit as n approaches infinity from the sum of the areas of all rectangles. All have the delta x as the base, but f of xi is different from I equals 1 through n. This is carved in stone, and this is exact. This is called Riemann Sum. It bears his name. He developed it. Yes, since this is a constant, you can put it in front if you want to. Like we did here. I put it outside already because it's all the same for all rectangles. It's the same number. I took it outside. So you can rewrite it if you'd like as the limit as n approaches infinity from delta x. It does not depend on I. It's just a constant. Plus. So when I is 1, I have the first height. When I is 2, I have the next height. When I is 3, I have the next height, till I finish all of them. And this is the exact. Okay. So now, the simplest example with the limit of the Riemann sum, let's go and calculate the exact area, because now we can. So previously we got 7/2 with the leftmost point, 7/4 with the leftmost point, 15/4 with the rightmost point, and 21/8 with the midpoint. And now let's get the exact area. There's 3 preps here, 3 preps. So the question here is, use the limit of the Riemann sum to calculate or determine the exact area under f of x on 0 to 2. For something like this, we have 3 preps. We have to start with the preps first. Okay, so here's the first prep. Preps. Mandatory preps. Number 1, delta x, no big deal. 2 minus 0 over n. 2 minus 0 over n. Prep number 2, xi. So I got this. Now I want to get this, and then I want to get this. And then I can put everything together. So this, this, and this. And then I can put them together and determine the limit. So let me explain the xi. Zero is here, 2 is here. That's our interval. And I divide in equal pieces. I know they're not equal, sorry. So I divided the subinterval, the interval 0 to 2, into n subintervals. At this point, if we have n subintervals and they go to infinity, it doesn't matter anymore if you'll use the height of the leftmost point, the height of the rightmost point, or the height of the midpoint. It doesn't matter. They're so close. So we're not establishing that anymore. It's not important at this point. If I have n and they go to infinity, it doesn't matter. So, but when I get to this point, I know that this is x1, which is 0 plus delta x. 0 plus delta x. In this case, that will be 0 plus 2 over n, 2 over n. When I get to this point, this is x sub 2, which is 0 plus 2 delta x, which will be 2 over n times 2, which is 4 over n. Can anyone give us the formula for x sub 3? This was x sub 2, this is x sub 3.
Zero plus 3 delta x.
Excellent. What I want you to give me is xi now. What is the formula for xi? Exactly. That's all I cared about.
0 plus,
Yes.
I delta x.
That's it. For 1, it was 0 plus 1 delta x. For 2, it was 0 plus 2 delta x. For 3, it was 0 plus I delta x. So then my xi is basically I times delta x because this starting point is 0. So this is 2I over n. Last prep. Last prep is f of that number. So f of xi is f of 2I over n. Remember, f of x is x squared. Can anyone tell us how much is f of 2I over n?
Four I squared over n squared.
Brilliant. That's it. We have all the preps now, the exact area, the limit as n approaches infinity from the sum. We can write the 2 over x, the delta x 2 over n outside or inside. Let's put it already outside. It does not belong inside. It's a constant. From I equals 1 through n from f of xi. Perfect. So now, here is another constant. It's a constant times I squared. I'm going to move this outside as well. How come? I'll find it today. Maybe. A constant goes outside, as long as it's a factor. If it's plus or minus, I cannot do that. I'm trying to keep them in the correct order, so I don't have to scan them twice. Okay, so then we have limit as n approaches infinity from 2 over n times 4 over n squared times the sum of I squared from I equals 1 through n. Or limit 8 over n cubed, n approaches infinity. But I know what this equals to. So this equals. I know what this is replaced or has to be replaced by. It's the ugly one from all those three. n plus 1, 2n plus 1 over 6. n plus 1, 2n plus 1 divided by 6. What now? Very simple. Simplify. Distribute. Of course, take 8/6 outside in the form of 4/3. Please always, always, always simplify. Limit as n approaches infinity. The denominator is only n squared. The numerator I can distribute. So 2n squared plus 3n plus 1. And now the concept of the limit, it tells me what to do next. What will I do next to determine this limit?
Use infinity for n.
Good. And what is the next step then? A procedure that we cannot forget or disregard because it's helping so much.
Wouldn't that be L'Hopital's rule?
Excellent. Very good. Very good. Still infinity over infinity. When I differentiate it, I get 4 over 2. Would you agree? Let's do it again. So this is 8 over 3. And this is the exact. And as expected, the midpoint was the closest. The midpoint has to be the closest. Now, because the function was increasing, we get this. But when the function is decreasing, we'll get this. It's not important. We're not going to need to do that or think in those terms too much, just to have an idea. I don't want you to expect that always the leftmost point will give an underestimate. No, I don't want you to expect that. Okay, so we are restricted when it comes to the limit of the Riemann sum. If you ask me to calculate the limit of the Riemann sum for a sine function or cosine function, I will not be able to. But if you ask me to show and illustrate the limit of the Riemann sum with a linear function, with a quadratic function or a cubic function, I can. I can determine exactly. But anything else, we cannot. Don't say tangent or arc sine or hyperbolic sine or anything else. I can only show the limit of the Riemann sum with linear functions, quadratic, cubic. So I like to illustrate with at least one more. I want you to make up a function and an interval. Now, the interval, as long as the interval is 0, a number, the calculations are much easier. But if you say the interval 1, 4, let me show you just for this function, then xi becomes 1 plus I delta x, right? So this will be 1 plus 2I over n. And when I plug it in the function xi, then this will be 1 plus 2I over n, everything squared. Well, this is more work because I have 1 plus 4I over n and plus 4I squared over n squared. And if the function is a cubic function, then it will take me 20 minutes. So if we keep the interval simple with a starting point at 0, then the calculations will be less cumbersome. But if we keep anything else at any other value, then the calculations will be more intense.